Hello and welcome to a brand new section of this course, Signal Processing. In this concise section, we will illustrate and explain the main foundations of signal processing. Now let's start with the first video of this section, where we'll analyze the frequency components of a signal with a fast Fourier transform. In this video, we'll show how to use a fast Fourier transform, or FFT, to compute the spectral density of a signal. The spectrum represents the energy associated to frequencies, or we could say encoding periodic fluctuations in a signal. It is obtained with a Fourier transform, which is a frequency representation of a time-dependent signal. A signal can be transformed back and forth from one representation to the other with no information loss. Here we'll illustrate several aspects of the Fourier transform. We'll apply this tool to weather data spanning 20 years in France, obtained from the US National Climatic Data Center. Let's import the packages, including scipy.fft pack, which includes many FFT-related routines. Next, we import the data from the CSV file, which has been obtained from this website. Now get back to the Jupyter Notebook and this line of code to load the data. Here we file as df0 using the read CSV function, and this is the URL. The number 9999 is used for NA values. The pandas can easily handle this. In addition, we tell pandas to parse dates contained in the date column. Now to view the data, let's type df equals df0 date greater than or equal to 1994 January and the first of the month, and check the top values with the head function. So these are the first 5 rows. Each row contains the precipitation and extreme temperatures recorded each day by one weather station in France. For every date in the calendar, we want to get a single average temperature for the whole country. The group by method provided by pandas lets us do this easily. We also remove any NA value with drop NA. Let's continue writing the code. df average equals df.drop NA and use the group by function on the date column. Also, we obtain the mean. Let's display the first 5 rows with the head function. And here's the output with the precipitation, Tmax and Tmin. Now in the next cell, add these lines of code. Here we get the list of dates and the list of corresponding temperatures. The unit is in tenths of a degree, and we get the average value between the minimal and maximal temperature, which explains why we divide by 20. Let's take a look at the evolution of the temperature by plotting the graph. We now compute the Fourier transform and the spectral density of the signal. The first step is to compute the FFT of the signal using the FFT function. Go ahead and simply type temp_FFT equals sp.fft pack.fft in parentheses, temp. Once the FFT has been obtained, we need to take the square of its absolute value in order to get the power spectral density. Here's a liner code to do that. temp_psd equals np.absolute value of temp_FFT to the power 2. The next step is to get the frequencies corresponding to the values of the PSD. Here's the line of code for this. The Fft Frequency Utility function does just that. It takes the length of the PSD vector as input, as well as the frequency unit. Here we choose an annual unit. A frequency of 1 corresponds to 1 year, or 365 days. We provide 1 by 365 because the original unit is in days. The Fft frequency function returns positive and negative frequencies. We are only interested in positive frequencies here, as we have a real signal. To resolve this issue, let's set I equals Fft frequency greater than 0. We now plot the PSD of our signal as a function of the frequency, with these lines of code. As you can see, the unit is 1 per year. Also, we choose a logarithmic scale for the y-axis, decibels, because the fundamental frequency of the signal is the yearly variation of the temperature. We observe a peak for f equals 1. Now we cut out frequencies higher than the fundamental frequency by executing these lines of code. Next, we perform an inverse FFT to convert the modified Fourier transform back to the temporal domain. This way, we recover a signal that mainly contains the fundamental frequency. Let's plot the graph to visualize this. As you can see, we got a smoothed version of the signal because the fast variations have been lost when we have removed the higher frequencies in the Fourier transform. Superb!